This talk will not have any proofs, but there will be lots of open questions, so hopefully that's okay. And all of this is joint work with Shichen, Anindya, Rocco, Servedio, who was my PhD advisor, and Eric Weinberg. So I'm going to break up the talk into 3 parts and just talk about this kind of work that I've been working on for the past few years. Starting with kind of complexity, and when you hear the word complexity, the first thing that maybe comes to mind is Turing machines and Boolean functions, and it's a little weird to see the word complexity sitting next to the word convexity. But over the past few years, there's been kind of a weird analogy between results, algorithmic as well as structural results for Boolean functions. So just to remind everyone, a Boolean function takes in a bit string of zeros and ones and outputs a single 0 or 1. So it's just an indicator of a subset of the hypercube. And there's kind of been this correspondence between monotone Boolean functions which, as you walk up the hypercube in Hamming weight, only increase, and convex sets in Rn, high-dimensional convex sets. And sometimes we require the sets to be symmetric for this correspondence to be clear. So just to give a little bit of boilerplate and just to convince you that monotone functions are well studied, we know a lot about their analytic structure, density increment results, learnability, things of this sort. These things show up in combinatorics, complexity theory, they're kind of all over the place. And you can ask the same questions for convex sets as well, except you have to make two or three minor tweaks. So, if you're talking about Fourier concentration, you replace the parity basis with the Hermite basis. You replace the uniform distribution with the Gaussian distribution. But one thing that's kind of become clear over the past few years is that often there's not only a qualitative correspondence, like not only can you prove similar results, but there's also a quantitative correspondence. Like the bounds you get for various things are often the same. And often the techniques used are just completely different. So just to give you one concrete example, which is also how we got interested in this work. We were kind of looking at this Quanta article about the Gaussian, at least I was looking at this Quanta article about the Gaussian correlation inequality. And it looks a lot like the Harris-Gleichmann inequality, which is something which we kind of learn in undergrad. So just to remind everyone, the Harris-Gleichmann inequality just tells you that any 2 monotone Boolean functions are positively correlated. Yeah? Kind of the intuition is that, for example, if you're thinking of a graph and you're told that the graph has contains a triangle, then the odds of it having a Hamiltonian path go up, right? These are positively correlated events. And this is kind of a very classic, very simple inequality. It was known in the 60s, and the proof is a 3-line induction. I'll even show you the proof in a few slides. But if you replace monotone Boolean functions with symmetric convex sets over Gaussian space, then the exact same statement is known as Royin's inequality, or the Gaussian correlation inequality. And this was open for over 40 years. And the proof is not, it's not a 3-line induction. It's much more than that. And so, kind of the question that got us started on this line of work was, well, both of these inequalities are qualitative inequalities. They just tell you that 2 things are non-negatively correlated. And can you ask for a better inequality? So just restating this, Harris-Gleichmann and Royin both tell you that monotone functions and convex sets are non-negatively correlated with respect to uniform and Gaussian measures. But can you hope for maybe a more meaningful bound, maybe in terms of some properties of the functions? Yeah. And so with this in mind, let's go back to Harris-Gleichmann. Harris-Gleichmann just tells you that these functions f and g are non-negatively correlated, and so we're going to try to prove it. And a natural way to prove it, especially when you're of the hypercube, like I said earlier, is by induction. So we're going to take these functions f and g and define restrictions. So let f0 be the function on the n-1 dimensional cube, where you just fix the last bit of f to be 0. And you can similarly define f1 and g1. Yeah. And so, so it's easy to check that, you just take you take the left-hand side of the Harris-Gleichmann inequality, and you can just expand it out and do a little bit of algebra and express it in terms of these restricted functions. This first highlighted term is nothing but the correlation between the restricted functions f0 and g0, so it's not negative by the inductive hypothesis. Second term is correlation between f1 and g1, again not negative. And the third thing is a product of two kind of interesting looking things. Let's just focus on the first quantity. Does anyone see what this is?
It's an average by how much it grows.
Yeah. So first off, great, that's a good point, but first off, it's also non-negative because f1 always dominates f0 because it's a monotone function. But this quantity, especially for monotone functions, is a very well-studied quantity in Boolean function analysis. It's known as the influence of the ith variable. Like in the previous slide, the nth variable. So just to remind everyone, given a Boolean function, you can define this natural isoperimetric quantity called the influence, which is the probability. So the influence of a coordinate direction I is the probability that a random input is sensitive along the ith direction. So you draw a uniform random x from the hypercube and you flip the ith bit and you see the probability of the event that the value of the function changes by flipping this one bit. It's a very natural isoperimetric quantity, and it kind of captures how much the function depends on this ith coordinate. There's been a long line of work built around this notion of influence. And so this notion of influence naturally showed up in the proof of Harris-Gleitman. So you might hope to actually get a quantitative version of Harris-Gleitman, which kind of takes, which lower bounds the correlation between two monotone functions in terms of these influences. And this is precisely what Talleyrand proved in 1996. So Talleyrand showed that if you've got two monotone Boolean functions, then the correlation between f and g is lower bounded by essentially the sum of the product of the influences. Yeah? There's this annoying psi function which is like x over log 1 over x. I don't care about the log factor too much, but it turns out you do need this log factor, so it's not an artifact of the proof. And Talleyrand's proof is difficult. It's like a 15-20 page long proof, and people have tried to simplify it over the past 20 years. There have been like many attempts made to simplify it. So just to summarize the situation so far, Harris and Gleitman showed that things are the correlation for Boolean functions are negative. Ryan showed the exactly analogous result for convex sets, symmetric convex sets. And then Talleyrand came along and robustified the thing on the left. And in 2020, 2021, Anindya, Rocco, and I, this was COVID, we gave an analog of Talleyrand's inequality for symmetric convex sets for Gaussian space. There's one caveat. Our dependence on we get a slightly worse logarithmic dependence, but the advantage is that this proof generalizes. So we recover, we give a simple proof of Talleyrand's inequality as well. It's about a page and a half long, except with a logarithmic factor, like an additional logarithmic factor. And you can also extend this proof to get quantitative correlation inequalities in a bunch of different settings. And the proof is very short and kind of uses tools from complex analysis. I'm not going to go into the proof, but I'm happy to talk about it anytime this week if people want. But I should tell you what these quantities are, these highlighted things. These highlighted quantities are the degree 2 Hermite coefficients of this convex set. The convex sets K and L. That interpretation doesn't matter too much. There will be a much more geometric interpretation, but really what matters is that these K tilde 2 EIs, whatever they are, they really do behave a lot like the Boolean influences. And so we spent a little bit of time trying to think about this notion of influence, and so let me tell you what these so-called convex influences are. So there's a couple of different definitions, but maybe the simplest one is a very natural geometric definition. Let's say you want to compute the influence of the first coordinate direction, so just E1 for the set K. You take the set K, you dilate it a little bit by a factor of delta along the direction you're interested in, and you look at how quickly the volume of the set is increasing. Since the set is symmetric and convex, this is always non-negative. It's not too difficult to see that. And so the influence is just the limit as delta goes to 0 of this of the difference in the volumes of this dilated set and the original set divided by delta. So it's just a derivative, yeah? And let me try to convince you that this notion of influence really behaves like the Boolean notion of influence. There's a couple of examples which are maybe helpful for the rest of the talk as well. So one simple Boolean function that we all know and love is the dictatorship. Just a projection onto the first coordinate. If I is equal to 1, then the influence is 1. Every time you flip a bit, the value of the function changes. And if I is not equal to 1, the influence is 0. And kind of the analog of the dictatorship turns out to just be a slab. Yeah, just a set which depends on one direction. Again, if you don't care, if you look at any direction besides the first direction, the influence of the set is 0. Another kind of natural Boolean function is the majority function, which outputs 1 if you're in the top half of the Boolean hypercube in terms of Hamming weight. And the analog of this turns out to be the L2 ball. You want to scale it to have radius root n so that the measure of volume is half. But the L2 ball of radius root n is the inner half of Gaussian space, just like majority is the top half of the Boolean hypercube. And again, if you do the computation, it turns out that the influences line up exactly in these two settings. Another Boolean function, which some of you might have seen, is the tribes function. So you have an AND of a bunch of disjoint ORs. There's a typo there, I'm sorry. There should be an AND of ORs. And you can do a calculation and see that the influence of each coordinate for tribes is log n over n. And since tribes is kind of an AND of disjoint ORs, AND looks a little bit like an intersection. So the analog turns out to be the solid cube, which is an intersection of roughly n orthogonal slabs. Yeah, everything I've done so far is imprecise and hand wavy, but this correspondence seems to work out for a bunch of different reasons, and I'm going to give you examples of that. But we don't have a formal way of going from one setting to the other, at least as of now. Yeah. Right. And I also wanted to mention that there's a basic property of Boolean influences, which is that if a function has 0 influence, then the function is, if a coordinate has 0 influence, then the function is independent of that coordinate. You just average it out, the function does not change. And it turns out that the same thing holds for convex influences as well, although it's much more difficult to prove. It kind of relies on the Braskamp-Lie inequality. So this notion of influence seems to pass at least two basic sanity checks. That 0 convex influence means that it's a cylinder that's along a direction. And you get analogs of these basic Boolean functions. And we also already saw that like the Cologrand type correlation inequality holds for this notion of influence. But it turns out that you can prove a lot more, you can say a lot more things about this notion of influence for convex sets. Sorry. Yeah, you can just say a lot more things, including you can prove analogs of the Kankalae lineal theorem. You can prove sharp threshold results, robust like density increment results like Pascal-Cortona, and like weak forms of Friedgood's-Hunter theorem for these convex sets. And the proof techniques are very different. Again, like KKL, Friedgood-Hunter theorem require hypercontractivity over the Boolean cube, but our proofs do not use hypercontractivity. We use like tools from convex geometry and Gaussian isoperimetry, like Braskamp-Lie inequalities, Borel's theorem, things of that sort. So there's no hypercontractivity, and the proofs are very geometric. So it's kind of an interesting correspondence between these two situations. And there's a lot to explore. There's like many structural results which we were unable to prove, and hopefully I can get people interested in some of these things sometime this week. But that's all I'm going to say about influences for now, and I'm going to jump to learning convex sets. So,
question.
Yeah.
So the inequality that your inequality that you proved. So the left-hand side is, I mean, you were working with Gaussian, which is invariant under rotation. But
Yeah.
your right-hand side is it invariant?
It is, yeah. It takes a little bit of work to see, but
Okay.
it is, yeah, rotation. So, good point. Maybe I should also note that if you in the Boolean setting, if you add up all the coordinate influences, you get like something that's called the total influence, and this is, this doesn't depend on the basis. And the same thing holds for convex influences as well. Again, you just add it up, you're just uniformly dilating the set, and the Gaussian is rotationally invariant, so it's not very difficult to see that. Yeah. But good question, thank you. Yeah. Any more questions? So this notion of influence will pop back a few times for the rest of the talk, but I want to give a few more examples of this correspondence.
Do you have a geometrical interpretation for this?
More geometric than what I had earlier? Or?
Yeah, like in terms of volume of boundary icons.
Oh, good point, yeah.
It's when you slice it and integrate.
Yeah, good question. So this was the notion of influence. So it feels a lot like surface area, right? And indeed, if you're adding, the argument over here is k plus like a delta-sized copy of k, the Minkowski sum of k plus delta k. But if you replace that delta k with a delta times a unit ball, then you just recover the Gaussian surface area. So if you know that your set contains a ball of constant radius, this is bigger than the Gaussian surface area. And one kind of hazy way to think about this is that this is a little bit like the edge boundary of a set, versus surface area is like the vertex boundary of a set. Again, this is hazy, but I can say more about this offline. But this is as geometric of an interpretation you can give. Yeah. He seems unsatisfied. I can talk to you after.
No, it just seems to me that it's equal to if you just slice it by line. And you define this point.
Oh, I see. You're saying do it line by line.
The boundary of the sliced
with
the surface area.
Yeah.
And just differentiate that zero. That seems to be
I think that's right. Yeah. You're doing it fiber by fiber.
Yeah.
Right? Yeah. Awesome. So yeah, many open questions for this notion of convex influence, and I think all of them are very interesting. One which I think is kind of cool is, again, in the Boolean setting, if a coordinate has influence epsilon, you average it out, you're epsilon close to a function which doesn't depend on that direction. But proving the same analog for convex sets turns out to be much more challenging, and you run into like stability problems for like Brun-Minkowski type inequalities, which are like difficult and deep. I don't know anything about them. Great. So I'm going to move on to the second part of the talk, which is learning. And this is stuff which I've been kind of thinking about more recently. So just to give a bit of background, for the problem of learning convex sets, you are given a convex set that's unknown to you. You're promised that the set is convex. And what do I mean by the fact that you're given a set? Well, you're given query access to the indicator function of the set. So you can give it a point x, and it'll tell you if a point is in the set or not in the set. And your goal is to draw a bunch of queries and then output an approximation to this unknown set k. Yeah? But for this question to make sense, I should tell you what it means to approximate a set by another set. And the distance metric we're going to use is going to come from the Gaussian. So given a set K and another set L, you look at the symmetric difference of the two sets, which is the pink error region over here, and you look at the probability of a standard Gaussian vector landing in this error region. So it's a very natural notion. And indeed, within theoretical computer science, we use this notion for testing, learning, de-randomization problems. So coming back to learning convex sets, let's say you want to point one approximation to this unknown set K under the Gaussian distance. Then it turns out that you essentially need n to the root n queries. And this is a result from 2008 of Clivens, O'Donnell, and Servedio. And so they tell you that if you draw n to the root n queries, you can output a function L, which does a pretty good job at approximating your set K. But there's one downside to their result. It's that this function L turns out to be a degree root n polynomial. In other words, you're trying to learn the class of convex sets using a class of non-convex hypotheses. There's like no reason why a degree root n polynomial is convex. So that's a little unsatisfying. And so it'd be nice if you could properly learn convex sets. And well, if you want to properly learn convex sets, you need a class of hypotheses which are also convex. And arguably the simplest such class would be the class of polytopes, yeah? In other words, intersections of half spaces. And this kind of naturally motivates the following question. In order to understand how well you can learn using an intersection of half spaces, you essentially also need to know how well you can approximate convex sets by an intersection of half spaces. And so this question of Gaussian polytope approximation comes up very naturally. So someone walks up to you with a convex set K. How many half spaces do you need in order to point-point approximate it under the Gaussian distance? And we're going to be interested in both upper bounds as well as lower bounds for this question. So by upper bounds, I mean generic results saying that every convex set can be approximated by some number of half spaces. By lower bounds, I mean explicit instances of convex sets which need a large number of half spaces to approximate. And so this is the only proof in this talk, but hopefully it's interesting. So it's not too difficult to prove an exponential upper bound for this problem. So let's say you walk up to me with this convex set K. First thing I'm going to do is I'm going to intersect it with a ball of radius root n plus 100. Because of a Gaussian space, all the action is happening within this ball. Yeah, like a standard chi-squared tail bound tells me that there's basically no mass, 0.05 mass, outside this ball. So I'm going to discard everything outside this ball and just focus on this new set K prime. By the triangle inequality, you just need a 0.05 approximation to K prime. And it turns out that 2 to the n half spaces suffice because what we're going to do next is we're going to use an off-the-shelf result which has the following guarantee. There's an off-the-shelf result of Dudley from the 70s, I'll state it in a few slides, which tells you that 2 to the n half spaces are enough to approximate your set K prime with the following guarantee. It turns out that the length of any point in the set L to the closest point in the set K prime is essentially 0.005 divided by n to the 1/4. Don't worry about the n to the 1/4, you'll see where that comes from. But this is kind of a classic off-the-shelf result for approximating convex sets under the Hausdorff distance. Yeah. But we don't want this sort of guarantee. We want a guarantee which controls the Gaussian measure of the pink region, right? But because of convexity, you could kind of take that little red line and slide it over the boundary of the set K prime to get this, this dotted region. And convexity tells you that the error, the pink region, is strictly dominated by this blue region. And now I'm just going to copy this over to the next slide. And we will show that this is less than 0.05. So I'm going to copy this over to the next slide, and we're going to do a little bit of calculus. So this blue region was precisely the set of points, x, which were at distance at most 0.05 over n to the 1/4. Yeah, I didn't write the n to the 1/4 in the previous slide, but hopefully that's okay. And you're just integrating the Gaussian density in this region to get the measure of that set. And we're just going to break this down into level sets. Yeah. So t runs from 0 to 0.05 times n to the minus 1/4. And now you're just integrating the Gaussian density along that level, along the boundary of that level set. And this second integral is a well-studied quantity in convex geometry. This is nothing but the Gaussian surface area of the set K prime, of this level set K prime sub t. And again, over here we look in the literature, and you can find a classic well-known result of Keith Ball, which tells you that the Gaussian surface area of convex sets in Rn is uniformly bounded by n to the 1/4. So this n to the 1/4 is why there was an n to the minus 1/4 in the previous slides. But you take this result of Keith Ball and you plug this in, and it tells you that you're integrating n to the 1/4 over an interval of width 0.05 times n to the minus 1/4. So this is at most 0.05. Yeah? So just putting everything together, you truncate, you kind of use this off-the-shelf result for Hausdorff distance approximation by Dudley, and you use Keith Ball's bound on Gaussian surface area, and you get that 2 to the O tilde n half spaces are enough to approximate any convex set under the Gaussian distance. Sure.
So we don't care about symmetry here at all.
This does not care about symmetry. Yeah. Right. I should have said this part of the problem and the next part don't care about symmetry. Yeah.
is there any reason to guess that symmetry could be an important, like it could help?
Good question. I'm not sure.
Probably not.
I would guess not, but I'm not sure. Any other questions right now?
But more general optics, the international optics is kind of polytope, but you look at the spectrum heat try to approximate the convex of the spectrum heat.
Not as far as I know, yeah, it's a natural question. Yeah.
I guess my thought about it is like, you spoke only about membership queries, but you have like separation oracles or something like that. You know?
Good, so I don't think people have thought about separation oracles in the context of convexity. People have thought about sample-based testing, and in this case, you need to learn. There's a tight lower bound one. So you do need queries if you want to, if you would hope to do something better. So if there's no other questions, I'm going to turn to lower bounds. Does anyone have a guess for what body might be hard to approximate? Right, so Puya's did that. So I think Puya's saying the L2 ball should be hard. And indeed, for all the other approximation notions, this question of polytope approximation, it's very well studied, and people have thought about it for the Lebesgue measure, the Hausdorff distance, like we saw, Banach-Mazur, blah blah blah. And it turns out that the L2 ball is extremal for all of these distance metrics. And so it's natural to think that the L2 ball would be extremal for the Gaussian as well. Yeah. And this is kind of where we tried proving this, and we failed. We couldn't come up with anything, and so we went to kind of this Boolean function analogy, and it ended up being kind of helpful to prove a lower bound over here. So I gave a few examples earlier, and you might have guessed this already, but an intersection of half spaces behaves a lot like a CNF formula. So, the intersection looks a little bit like an and, or is a little bit like a slab or half space, but just to introduce some language, I'm going to call an or of variables a clause. Also, in case people aren't familiar with CNFs, these are just depth to Boolean circuits, take in bit strings, output a bit string, and function or function. Hopefully people have seen this stuff. Stop me if you haven't. But, okay, great. And so kind of this question of polytope approximation is analogous to the question of approximation by CNF. But let me tell you what approximation by CNF means. It just means approximating a Boolean function by a CNF with a small number of clauses under the uniform distribution. And so, whoops, sorry, I skipped a slide. Given a Boolean function, this question of CNF approximation asks how many clauses you need to approximate the function f by a CNF G, so that the error is at most pointed under the uniform distribution. So the number of half spaces for this polytope question corresponds to the number of clauses over here. And just coming back to this question of polytope approximation, we know that the L2 ball behaves a lot like majority, right? And it turns out that this question of CNF approximation for the majority function has been studied before. So this thing is known over here. In particular, there's a lower bound which goes through this notion of influence. Yeah. So again, we saw earlier that the influence of each coordinate on majority is 1 over root n. There's this quantity which is the total influence, which is just the bold I of a function, which is just summing up all the individual influences. And for majority, total influence is on the order of square root n. Yeah. And it turns out there's a structural result which Hostad and Bopanna proved in the 90s, which says that any S-clause CNF, so if you've got a CNF which is an AND of S many ORs, its influence is bounded, its total influence is bounded by order log S. Yeah? And so you take the fact that majority is influence root n, and you do a little bit of Fourier, you just use like Parseval's formula, and you kind of have to use monotonicity as well. And it tells you that you need 2 to the root n clauses to approximate majority. find S clause. You need 2 to the root n clauses to approximate majority by CNF to accuracy 0.1. And you can kind of take the same kind of template and execute it in the convex setting to get a mildly exponential lower bound for the L2 ball. So you take this notion of convex influence, which we talked about earlier. You prove this Hausdorff-Papanna analog. In the Boolean setting, you prove it using the switching lemma, very combinatorial proof. But our proof is again geometric, and you use Gaussian isoperimetry again. But you get the same statement. If you have an intersection of S half spaces, the total convex influence is order log S. And again, you have to use Fourier and convexity behind the scenes, the same way you use Fourier plus monotonicity. So again, very different settings, very different techniques, but the same kind of proof kind of comes out. Joe? Yeah.
So do you have some, is there some like random restriction that's still happening in Gaussian space, or?
Not in this proof.
Can you pull ideas from this proof back to?
Not as far as we know. Yeah.
So just
Good
totally,
question.
totally
different proofs. Yeah. So to summarize the situation so far, we know that a generic convex set needs an exponential number, can be approximated with an exponential number of half spaces, and we know that the L2 ball needs 2 to the root n. And you might think that, well, the three of us, this is work with Anindya and Rocco, we were lazy and we were just trying to not think hard enough, and maybe you can boost this lower bound to an exponential lower bound. But let's actually see what happens for majority for CNF approximation. Because the analogy told us something, it gave us some sort of a lower bound. So let's go back to the analogy and see if there's non-trivial upper bounds, non-trivial approximators for majority. And it turns out that, again, things are known over here. So there's this paper by Brian O'Donnell and Carl Wimmer from 2007. It's titled Approximation by DNF. Just pretend the D is a C. It doesn't make much of a difference. But they say in the abstract that for any constant error, there is a CNF of size 2 to the root n that approximates majority. So in particular, this tells you that the Hausdorff-Papanna type of argument was tight. There's a matching upper bound construction. So just to restate this in bigger print, bigger font, O'Donnell and Wimmer showed that there is a 2 to the root n clause CNF that approximates majority to accuracy 0.1. Let me tell you what the O'Donnell-Wimmer construction is. So O'Donnell and Wimmer take an AND of roughly 2 to the root n, I'm hiding epsilon dependence, roughly 2 to the root n randomly drawn clauses, and each clause has width root n. You draw root n variables at random, and you repeat this process 2 to the root n times. And they show that on average, there's some function in the support of this. On average, the error you incur from under this probabilistic construction in majority is at most 0.1. And so there's some function in the support of this distribution which approximates majority. And you might ask, okay, it's time to execute the same template in the Gaussian setting. And it turns out that this has actually been done before. So the analog of majority is kind of this well-known extremal convex body due to Nazarov. Just for context, we saw this theorem by Keith Paul, which says that the Gaussian surface area of convex sets is uniformly bounded, and Nazarov's construction actually matches that upper bound. So Nazarov's motivation in coming up with this body was to give a convex set with maximal Gaussian surface area. And it turns out to be useful for us as well. So just like the O'Donnell-Wimmer construction, we AND together, or intersect together, roughly 2 to the root n half spaces. Each half space is at distance roughly n to the 1/4 from the origin. So half space is defined by drawing a random Gaussian. This is typically length root n. The threshold is at n to the 3/4, the distance is n to the 1/4. Okay. So let's look here. And in order to control this error region, you kind of use the same idea. Again, the math is different, but I guess the main intuition or philosophy behind this construction is the same. Yeah. So it turns out that the L2 ball has a sub-exponential complexity, sub-exponential facet approximator for this problem of polytope approximation. And this is already kind of surprising for us, because for almost every other distance metric, or for every distance metric that we know of, the L2 ball needs an exponential number of faces. You're essentially constructing an epsilon net, and you need 2 to the n points or something. And so this kind of naturally makes you wonder if there is a convex set which needs an exponential number of half spaces to approximate. And we tried thinking of one, but we decided to be lazy and keep reading this paper by O'Donnell and Wimmer. And so if you keep reading the abstract, they actually say that there's a monotone function. You can forget the sentence about total influence, but there's a monotone function such that any CNF or DNF that 0.1 approximates it requires essentially an exponential number of clauses. So again, just putting this in big font, O'Donnell and Wimmer give a monotone Boolean function with an exponential lower bound for this problem of CNF approximation. This is great. It's an unconditional lower bound. We love it in complexity theory. It's also monotone, so it kind of fits with the analogy really well. And the key idea over here is this notion of random projections, which complexity theorists ended up using later to prove some very nice circuit lower bounds. But O'Donnell and Wimmer's hard function is something which we've actually kind of seen before. The hard function they use is the tribes function. So it's an OR, but it's not the tribes function we saw before. The tribes function we saw before was CNF tribes. The function they use is DNF tribes. So it's an OR of a bunch of ANDs. You have roughly n ANDs, and each AND is on roughly log n variables. And this function is DNF tribes. And we know what the analog of CNF tribes is. Yeah, we said it's a solid cube. It turns out to be extremal for the same inequalities, so on and so forth. This kind of naturally motivates this question of what the convex analog of DNF tribes is. And so, just to kind of try to blindly follow the analogy, DNF tribes is kind of related to CNF tribes, and these are, if you look at chapter 1 of Ryan O'Donnell's book, these are Boolean duals of each other. We know what CNF tribes is. We know that it behaves a lot like the L infinity ball. And the word dual is maybe suggestive. There's a very natural notion of duality in convex geometry, which would tell you that the dual of the L infinity ball is the L1 ball. Yeah. So this was very compelling to us, and so it indeed makes some sense because the L1 ball in n dimensions would indeed have 2 to the n half spaces. Each of them is in one orthant. It's not as symmetric as the L2 ball. So in our L2 ball upper bound, we really exploit the symmetry of the L2 ball and the Gaussian, and this kind of breaks that symmetry as well. So all the signs were kind of positive, and we spent a lot of time trying to prove this upper bound, trying to prove a lower bound here. But then it turns out that there's actually a sub-exponential approximator for the L1 ball as well. So, so it turns out that 2 to the n to the 3/4 as many half spaces suffice to approximate the L1 ball under the Gaussian distance. And the construction is again probabilistic. It's very distinct from Nazarov's construction for the L2 ball. The main idea is to sample very large L1 balls in low dimensions, take juntas or cylinders of these L1 balls and intersect them. And the analysis is actually kind of annoying and long, and it's a little technical. We end up needing to control the sums of independent random variables far out in the tail. And kind of the standard trickery, you use Gaussian tails and Hausdorff Gaussian tails by Berrier-Sein fails because the error in Berrier-Sein is too much. You get you eat 1 over root n error, and that's just too bad for us when you far out in the tail. And so kind of a cool thing which I didn't know about before this project is there's these multiplicative Gaussian tail bounds, which are useful to control these sorts of things. They've been known since the 70s or 80s, but I didn't know about them until last year. Right, so to summarize the situation so far, we still don't have an example of a convex set which needs an exponential number of facets to approximate. You might ask if there's a lower bound for the L1 ball. If you use this notion of influence again, you get a 2 to the root n lower bound. There's a gap over here. We think the upper bound should be 2 to the root n, but this would require us to open up the Kramer type large deviation bounds machinery. But there's another reason to not want to do that, which I'll get to in a second. So you can take this construction for the L1 and L2 ball, and it's natural to ask if it works for LP balls. So it turns out you can generalize the L1 ball construction with a bit more work, like a few pages of work. We work for LP balls for p between 1 and 2, but then this breaks at p equals 2 because we can't apply those Kramer type large deviation bounds. So that maybe suggests that this is not the right construction, and maybe there's a different way to do it, which would give you a 2 to the root n upper bound for LP balls. And indeed, as p goes to infinity, this should only get easier, right? When p is infinity, you have linear in n number of faces. It's a cube. And our proof does not take that into account. And there's much more stuff we kind of found about this problem of polytope approximation. We found connections to average case. You can prove like average case lower bounds in the sense that some number of half spaces are needed to get accuracy at least half as epsilon, as opposed to accuracy 1 minus epsilon. So you can prove these sorts of things, and there's connections to weak learning and pseudo-randomness, theories of polytopes, things of that sort. But again, there's lots of open questions over here. We don't know what the correct upper bound is. We don't know if there's a convex set which needs 2 to the n half spaces, or if every convex set has sub-exponential number of half spaces. It can be approximated by sub-exponential number of half spaces. Maybe an easier question is to generalize the construction for LP balls. This should certainly be easier, but we don't know how to do it. And another question which we can't say anything about right now is approximating convex sets by a small number of points whose approximating convex sets by small vertex approximators. So you have a bunch of points whose convex hull is the set you use to approximate the original set. And for other distance metrics like Hausdorff, Banach-Mazur, if you have a tacit approximator, if you have a polytope, you kind of get vertex approximators for free just by passing to the dual. But over Gaussian space, you can't quite do that because you can have a set of measure 0 when you take the dual. You can end up with a set of measure 0 when you take the dual. So it doesn't quite work out super nicely. This question of polytope approximation ended up being super useful for 2 more things, which, oh yes.
Yeah, I just wanted to ask, so if you sort of looked at the most general formulation and say you just want to find any convex set which is close to this convex set, instead of like approximating this by polytopes, is anything known about that?
You can do this in 2 to the n time, I think.
Okay.
Yeah.
And that would be sharp, or?
It's not known. It's not known. Yeah. Okay.
You got the L1 ball as a kind of analog of the DNF case by duality. Is there a way to directly see it from the DNF ball?
Great question. So you're kind of pointing to the fact that the analogy is broken right now, because this is how we got to the L1 ball. DNF tribes as an exponential lower bound. We don't have an exponential lower bound. So this might not be the right way to get to. I think this is probably not the right thing to do. Yeah. Awesome. Any other questions about this stuff? So the last 10 minutes I'm going to talk about, last 5 minutes really, I'm going to talk about something slightly different. Okay. So this question of Gaussian polytope approximation ended up being useful for 2 completely kind of unrelated things. First is this problem of sparsifying Supremov Gaussian processes. The preprint will be on arXiv in a week or 2, but Rocco talked about it exactly 3 weeks ago in this very room. You should go like the video, leave comments. But I'm going to tell you a little bit about this problem of convexity testing. This again brings me to the third part of this talk. So the problem with convexity testing is, it's a very simple, very basic question. You're given access to an unknown set. You don't know if it's a convex set, but you want to determine if it's either convex or if it's far from convex under the Gaussian measure. Again, black box access to the set K. How many queries do you need to distinguish with constant probability between K being convex versus K being 0.1 far from every convex set? And the only upper bound we know is by learning. So if you can learn a function, if you can learn a set, then you kind of have you essentially have an explicit description of the set. You go off in a corner and you try to figure out if it's close to convex or not. So learning gives you an upper bound, and the same paper of Clyden's, O'Donnell, Servedio is the result you can use. So this is a 2 to the root n query algorithm. And this question of polytope approximation, we ended up using a lot of the ideas from there, and in particular this approximator for the L2 ball to construct hard instances for this problem, which allowed us to give the first polynomial lower bound for this question. So we can show that you need n to the at least some constant number of queries to test convexity. And you do this by taking the Nazarov body construction, kind of embedding violations of convexity, and showing that some distribution is indistinguishable from another one. I can say more about this offline. A one-sided algorithm, in case you care, is one which must always accept a convex set. Two-sided means it can make errors. Adaptive means it kind of, non-adaptive means it makes all this, it decides the points it's going to query in advance. Adaptive means the next query can depend on the answers received so far. All of that doesn't matter so much, we just prove the polynomial lower bound. But there's a big gap over here, and this is a nice question, and I wish we could make more progress on it. We are able to say something slightly stronger for a variant of this question, which is, can you estimate the distance to convexity of an unknown set? So someone walks up to you with this black box, and they ask you, how close is it to being a convex set? For this question, you can prove a mildly exponential lower bound of 2 to the n to the 1/4. This question is known as tolerant testing, so estimating the distance to having a property. And again, just to kind of connect this back to monotonicity, and so we can come full circle, the learning upper bound is again n to the root n, the classic result from 1996. You can prove a very similar tolerant lower bound, and indeed we proved this last year. But the testing complexity has been pinned down to be polynomial. So for monotonicity, we know that theta root n samples are necessary and sufficient for non-adaptive at least, to test monotonicity. And so it's kind of embarrassing that for the convexity testing problem, there's a big gap between polynomial lower bound and essentially exponential upper bound, but for monotonicity, we've pinned this down exactly. Right, so just to recap, there's a lot to explore, a lot of these structural results for this notion of convex influence. This question of polytope approximation also seems to have a big gap. It turns out you can properly learn monotone functions. This is recent work of Jane Long, Rubenfeld, and Vasilian. So it might not be hopeless to try to properly learn convex sets, I'm not sure. But again, I think understanding this polytope approximation question is a precursor to that. Finally, there's this question of testing convexity. There's a big gap. One thing which might be interesting is to try to rule out specific tests. Like, what if you just pick 3 points on a line, pick 2 points and pick a point between them, and if you don't detect a violation of convexity, you just output yes. Like, can you rule out this specific test? We don't know how to do that, so it might be interesting. And I think I have 5 minutes left, so I'm going to stop here. Thanks for listening.